All right, why don't we go ahead and get started. So good afternoon and welcome to the Scripps Technical Forum. I am Douglas Alden. I'm the lead engineer with the Center for Western Weather and Water Extremes here at Scripps. In addition, I function as the STF chair and get assistance setting up and running STF from my colleagues here on campus, Gwyn Nero and Vanessa Scott. Gwyn is the Director of Corporate Affiliates, Business Development, Industry Outreach, and Innovation, and Vanessa is an Industry Relations and Innovation Analyst. If you missed any of our recent presentations, you can find them on the Scripps Technical Forum playlist on the Scripps Oceanography YouTube channel. And just want to let you know that, whoops, I lost my sharing. Sorry, we'll get back to that. 1 second. So touchy mouse. Anyway, so we're recording. Just want to let you know that you've been muted. And if you want to ask a question during the presentation, you can use the Q&A function of Zoom. You can also hit *9 on your phone. You can also raise your hand if you'd like to speak your question. I think we discussed with Marcus Lehmann, who's going to be giving the presentation today, about having maybe reserving some of your questions for the end, but please feel free to jump in whenever. And if you have any problems with Zoom, just send a message to chat and we'll take care of it for you. So with that, go back here. So today we have a presentation by Marcus Lehmann from CalWave. They were out a couple years ago and gave us a presentation on what they were intending to do, but CalWave is going to provide an update on the U.S. Department of Energy funded R&D project for an open ocean pilot program for a wave energy converter to be placed off Scripps Pier starting in the third quarter of 2021. And with that, I'll hand it over to Marcus. Thank you.
Thank you, Douglas, for the introductions, and thanks everyone for joining and your interest in an update on our project. And I'll share my screen here. Yeah, with a year of delay due to COVID, we're finally picking up the work for our DOE-funded open ocean demonstration off the pier. So as a brief summary and kind of framework of the project, we're planning to install the buoy in mid-August, working with the dive team, Christian McDonald and Brett from the team here. We've installed the anchors last September, 4 gravity anchors around 1,000 feet off the pier, and then planning to operate the device for about 6 months, until the equipment is being removed. The device is around 15-foot buoy that's operating fully submerged in around 26-meter water depth. And so for today, next to the update, also we want to offer discussion of potential collaborations around that project, as well as potential equipment usage, co-usage during or after the project. And general thank you to our partners, main sponsor, of course, the U.S. Department of Energy Water Program, and then the collaboration with Scripps Institute of Oceanography, and as well as then PNNL and the other national labs and UC Berkeley. So some more details to the actual pilot location. We're pretty much southwest of the pier, extending the pier a little further south, and planning to have a umbilical cable laid on the floor to our demonstration area. And we have 4 gravity anchors on the corners being used to moor the device. We have an additional backup safety line, just as a parallel layer of safety to really make sure we secure station keeping of the device at all times during deployment. And we're collaborating with the Pacific Northwest National Lab, the Triton initiative there, and yeah, also DOE funded. They added additional sensor and testing to our project. They will deploy an integral noise spotter buoy, a short-term deployment, a drifting hydrophone, also short-term deployment, as well as 3 long-term bottom-mounted hydrophones to measure the acoustic profile of the device and operations, as well as a bottom-mounted 3D camera for some of the sediment investigation and general visual tracking. And so briefly to my background, I started working in renewable energy back in 2015 as a final project of my high school time. I built a solar race car, learned about the IPCC and climate change, and then really decided to focus my career on developing solutions to tackle climate change. Started mechanical engineering. And that path led me to ocean-based solutions to tackle climate change. This is a really great graphic showing the carbon sequestration potential of the different solutions. And here, ocean-based aquaculture, seaweed farming, and ocean energy offer an enormous amount, with up to 2 gigaton of CO2 sequestration. And this is from the report of oceanpanel.org. And the IPCC also found from a pure life cycle emissions perspective that ocean energy has the lowest amount of emissions per kilowatt hour produced, so significantly lower than, for example, rooftop solar at 17 from an infrastructure perspective, and then on the lowest even at 5.6 grams CO2 per kilowatt hour. And that's another motivation for us that this could really be a long-term provider of clean energy at the lowest emissions. And here a latest map of the ocean energy potential in the US that was published last year by the Department of Energy. And we can see that the total technical potential, so that already excluded impractical locations, still offers up to 60% of US electricity demand, and wave power alone, the light blue area here, up to 30% of electricity demand. And we can see available predominantly along the West Coast, but also East Coast and Alaska. And general additional advantage of wave power next to the higher energy density and the lower emission profile is the stable and abundant nature of the production profile. So we can produce power at night as well as winter times, which is a great complement to the wind and solar production profiles. And one of the big challenges to actually find renewables that can secure 24/7 all year long access to clean energy. And offshore wind is now finally also progressing in the US. Here, kind of the different architectures from fixed to floating. Mostly we've seen around 28 gigawatts globally in fixed bottom offshore wind, but now also floating, especially for the West Coast in the US here. Floating technologies will be required. And here, general map of offshore wind in the US, current BOEM lease areas, as well as areas under investigation. And I think this map is slightly outdated. There are 2 or 3 areas on the West Coast in California that are currently being investigated for floating offshore wind. For floating offshore wind, there's still different architectures. This is also UC Berkeley developed platform from Principal Power, kind of adopted from traditional offshore industries, as well as other concrete-based forms or spar-type technologies. And not that long ago, it wasn't actually clear how the dominant design in wind power would look like. Until then, really the 3-blade upwind design emerged as the dominant design because of 2 main features the architecture embeds. One is the high energy production. We can see from the theoretical limit that wind can achieve The 3-blade is really the closest to that efficiency. And I think with modern turbines, we're already seeing over 50% efficiency compared to the other architectures. And the second then that really led to the growth of the industry as a whole is the ability to shut off in storm conditions. So once a certain cutout speed is reached, the turbines are capable of effectively shedding loads on a hydrodynamic level, so turning the blades as well as the entire nacelle out of the wind with pitch and yaw control. So these are kind of the two critical features for any hydrodynamic renewable energy device. And so for wave power, we're still lacking such a technology, on a high performance perspective, as well as then that ability to shut down, which is for wave power even more critical as these storm events are significantly more severe than the largest winds that the turbines are experiencing. And on top of that, it's really a multi-domain challenge next to power capture and conversion and control. We have to meet reliability, survivability, installability, manufacturing, and then of course cost. So this is really a complex multi-domain systems engineering challenge as a whole. And as a brief update on the different types of ocean energy, next to wave, there is tidal stream, tidal range, OTEX, so ocean thermal, and saline gradient. Wave is a little behind in terms of commercialization next to tidal stream, and tidal range being the most advanced at the moment. And general and latest statistics from 2020, we're now at around 36 cumulated installed capacity in megawatt for tidal stream, and around 20 in wave power. And here's some latest projects, international, but also in the US. On top, this is the Verdant Power tidal turbine installed in the river in New York, as well as ORPC in Alaska, and a latest installment in Canada as well, with a floating technology similar to Orbital Marine. They also installed their latest turbine last year. I think it's a 2 megawatt turbine, so a megawatt per blade, as well as then Atlantis Resource Corporation in Japan with a first tidal project there. And for wave, it's not as clear in terms of architecture. We still have 3 very fundamental different types: point absorber, attenuator, and terminators. And then there are all kinds of ways you can convert the actual motion into power. And as said, these are still to be determined, which turned out to be the most cost effective. Here's some of the latest projects: a compressed air system that was installed last year in Australia, kind of a rotating, these are rotating mass devices where either water or a mass rotates, generates energy. This was a device installed last year as well, more of the attenuator type. This is a bottom mounted flap. And again, this is a compressed air system in the US that's currently, I think, in Hawaii on anchor and waiting to be deployed. And with that wide range of different technologies, the Department of Energy started the US Wave Energy Prize in 2015 to identify a technology that is really cost competitive and scalable to secure. So our team entered back then. We contested in a 1 to 50 scale laboratory test. This is from our test in Iowa in 2015, I want to say. And then we got invited to test at the top 10 technologies, tested then at the largest Navy tank in 2016. And our team did really well and was able to exceed the threshold and was awarded by the competition. So we're, the initial 4 of us with Nigel, Brian, Thomas, and myself in the Wave Energy Prize. And then Dan joined us in 18 and Josiah in 19. And really the core expertise we've developed are 6 to 7 technical areas. Next to resource analysis, hydrodynamic modeling is really the core, and that is boundary element method, time domain simulations, as well as high fidelity CFD simulations, experimental validation of these hydrodynamic models, and then the implementation of the controls of the actual technology. So how can we best convert, lead to the highest performance based on how we operate the device. And so we call that a digital twin we've developed in time domain. And then for the actual equipment, we've designed computer-aided design, dynamic models, and then actual physical implementation of that in a controlled environment. This is at our bench facility at UC Berkeley, civil engineering. And then we run this time domain simulation that then informs the actual actuation part here, that then drives our generator as it would be out in open ocean. And we can measure the response and performance. And that again informs the actual simulation. And so this is an example video here from our bench. Here's our time domain simulation that informs the actuator, that really simulates the behavior of the system in an ocean condition. And then we measure the response and performance as well as control that then gets informed into the simulation again. And so we have a sophisticated setup here that's also being used for earthquake, structural testing, kind of hardware in the loop setup. And this work has been done under a 2017 DOE award as a follow-up to the Wave Energy Prize. And then 2019, we secured 2 additional awards to work on a second larger system. And we're supported by the Sustainable Ocean Alliance, Breakout Labs, as well as the Autodesk Foundation, High Tide Foundation, and last year, 2020, this year, PacWave, the first, it's really a major milestone for the wave energy industry in the US. It's the first grid-connected 20 megawatt test site in Oregon, located off Newport. And they just received their FERC permit to connect to the grid, as well as their BOEM permit. And they're now actively working on installing the test site. I think the vision of DOE is is here tested next to each other side by side. So there are 4 berths of 5 megawatt each. Up to 5 devices of a megawatt or larger will be able then to be connected. And there will also be 1 berth secured for blue economy applications. So that could be interesting for some research, as well as there is pre-installed infrastructure and cabling to the site. And it's on the state of the science report, led in the US by the Pacific Northwest National Lab, collecting all the environmental effects of marine energy on the environment. Here led by Andrea Koping. And there was an updated report published in 2020, really showing the latest findings of all projects that are being recorded globally. And they're also collected on Thesis, the platform for findings here. And as a brief summary, again, the 6 risks for marine renewables to the environment is collision risk, underwater noise, EMS, physical change in habitat, and then entanglement. And the report applies a risk score here and then recommends follow-up actions. Here the highest scoring risk is collision, and that is predominantly caused by tidal current and offshore wind that are using blades that are moving faster than mammal often can see. And then they fly into wind turbines, for example, and that leads to a collision event. For wave power, specifically for our architecture, we only have slow moving part, drag based. And by that, we actually expect that risk to be very low and acceptable. And then another concern that's often being brought up is entanglement. And here, I think the main challenge is not so much the actual cables or mooring lines, but more that loose fishing gear gets entangled into these lines. and then a marine mammal get entangled into that fishing gear. So there are solutions, companies working on tracking lost fishing gear, preventing that. But I think it's also important for the developers to keep a close eye to prevent exactly that kind of entanglement to their mooring lines. And yeah, the PNNL is also conducting general simulations just to see the dynamic interactions and physical comparisons between, let's say, in this case, a 3-point catenary floating offshore wind and a humpback whale, as well as then the cable interactions, and found that just the dimensions, these cables are so large and stiff that the cables themselves have very low risk for entanglement. And next to these, the Department of Energy has an initiative called the Powering the Blue Economy initiative. And there they're investigating how marine renewables could support specific niche markets. One is power at sea, mostly I would expect most interesting to the Scripps community. Here, ocean observation and underwater vehicles. As well as then coastal communities, isolated microgrids, as well as disaster recovery, and then just seeing how these compare to distance to shore. We're seeing ocean observation underwater vehicle will be further out and less, having less of a chance to actually have a cable from shore to sensor packages. And here just some examples from that report. Ocean observation can be supported by marine renewables, providing power for navigational aid or powering sensors. Another example here, the harmful algae bloom tracking system, that could be upgraded with built-in power recovery from wave power next to traditional solar and micro wind. And here a good overview of different sensors the report has found, and these can be from ambient monitoring to communication, computer systems, navigational light, station keeping, onboarding maintenance, and inspection. So that's a pretty comprehensive list of sensors being used in ocean observation that need power, and then the same with underwater vehicles, as well as their charging stations to conduct long-term permanent resident studies.
But we lost our presenter there. Give us a few minutes and we'll get him back. You're back now. All right, great. Thanks, Marcus.
Sorry about that. My Zoom crashed. That has not happened to me before. On what slide did you lose me?
Yeah, that's a good question. I don't recall right off the top of my head where we were in the presentation.
I see.
I would go back to, looks like maybe slide 41.
Okay, I see.
Perfect.
Sorry about that. Yeah, so one of these applications as part of the Powering the Blue Economy from DOE was the Ocean Observing Prize, hosted by NOAA and the DOE. So we contested with a concept in the first phase, the discovery phase, and were awarded there for our xNode solution. The xNode being a IoT platform for long-term ocean observation, utilizing our wave power generation system to recharge onboard batteries, but can also be upgraded with solar and wind, and can be used for all forms of sensors. We have a variable payload compartment with access to the surface as well as above water, and can really be equipped with all forms of sensors being of interest for long-term studies. And then we can compress data and export it via satellite or 5G by now. Another application could be to charge drones for permanent resident long-term studies. And then coming back to our deployment under the DOE award, Yeah, we started out with a more detailed mid-ocean analysis using the CDIP buoys here indicated in the map, and conducted a hindcast analysis and wave rows analysis just to be sure we know where the waves are coming from. We're essentially right off that plateau here before the canyon, and so the waves predominantly coming from the northwest direction. Yeah, will travel over the canyon and then reach the test area. And that data was used to also predict on an annual profile, so showing kind of the most severe month expected, as well as then a longer hindcast analysis for safety, just seeing what were the most severe events over the last 50 years. And we can see one of the largest waves recorded were 5 to 6 meters here in the last 50 years. And next to that hindcast analysis, we started also a local time series with Marine Labs. They donated one of their Coast Guard buoys, as we see here on the bottom right. And so we were able to record real-time data last year and this year, including the storm from March earlier this year, where we recorded a pretty large 2-meter wave here that came in and was recorded right off the test area. And yeah, that finding and all that data collected was also used for a publication at the European Marine Energy, UTEC, European Wave and Tidal Energy Conference, called High Fidelity Coast Guard Buoy Data, supported a WEC demonstration at Scripps Pier, and yeah, showing exactly the areas we've environmental monitoring areas we've investigated, and then compared to the CDIP recordings as well. And so going forward now, we're planning, once the assembly of our system is completed later this month, we're planning to ship it to the Driscoll Marina in Mission Bay, and then mid-August in collaboration executed then by the diving team and the baster, tow the device to location and anchor it on site. And I think then plan to operate it for the 6 months test duration. And so I think with that, glad to open it to the Q&A session now.
So we had a question from Isabel K, and she asks, is the location essential? If the array extends south of the line directly west of the foot of the pier, it will be in the Matula Hual State Marine Reserve, where I suspect deployment is less acceptable than in the SD Scripps State Marine Conservation Area, in which the pier itself is located. So to go back to our early question, it's just, is the location essential on that site?
Maybe I'll jump back to the map. Yeah, so initially, kind of historically, how the project developed was that I was looking for wave data, and many years ago by now, I got introduced to Julie Thoma from CDIP, and was just looking for near shore data and SWAN models essentially. And then Julie mentioned, or essentially invited us and said, hey, why don't you come down here, because we have all that historical data and many years of hindcast data, which makes the deployment significantly safer, because we can actually design for these extreme events that happen once in a while. And so that's how kind of that historically came together. And that area was recommended in collaboration with Scripps as the best site for that short-term deployment. So yeah, we followed the guidance then from the local hosts that suggested that area.
Yeah, and then there was just another point was that the graphic in slide 47 was generated by Randy Bucciarelli. I'm sorry about name pronunciation, but anyway, he was wondering if you guys could attribute that graphic when you give these make any presentations.
Certainly, yeah, I borrowed that slide from our DOE updates that were internal, but yeah, I'll make sure for give a credit to the origin.
Great, yeah, and then let's see, we got Alexander's asking, long-term, is the vicinity of the Scripps Pier a viable area for larger scale wave power? Would UCSD have the ability to install wave generation for campus electricity generation?
That's a difficult question. I would probably, from a first gut reaction, I would say most likely not. This is an area dedicated for research. And yeah, getting the permits like PacWave did in Oregon takes a lot of stakeholder engagement and permitting and siting and you know, making sure all local stakeholders are involved. Potentially further out in the long run, but yeah, I think as of now, I'm not aware of any grid connected projects that are being investigated. There was a study done by a group around San Obispo, University of San Obispo, and they looked at the pier at Vandenberg, and yeah, that was essentially also a contestant for the grid-connected wave farm, similar to PacWave, and so they've done, I think, the most advanced work in California next to Humboldt Bay. PG&E did a study called Wave Connect, where they looked into a farm similar to PacWave many years ago, but yeah, I think the most likely site would be off Vandenberg.
Nice. All right. Well, at present, we don't have any further open questions, but with that, I'd like to thank Marcus Lehmann for giving us this update on CalWave, and appreciate the time today and everyone joining in with their questions.
Yeah, thanks again for hosting us, and said, yeah, we'd be glad to follow up also offline. Yeah, please send us an email at marcus@calwave.org, and yeah, we'd love to discuss potential collaborations around the project. We'll be testing, yeah, a set for the next 6 months, and then also have yeah, potential equipment that is very suitable for that site where we might not have a usage for it later. So we'd love to put that to use for scientific projects then going forward, including the umbilical cable, for example, or some of the other mooring parts. So yeah, we'll be most likely parts of our team will be there full time from August on, and there will be opportunities just to connect, stop by, and we'll be sitting. I think Christian assigned us a container at the top of the pier, so we'll be most likely there in person. So always glad to connect in person as well, and always welcome to tour the facility.
Great. Well, thank you. And everyone, just enjoy your day.
Thanks again.